like we'll start with linear algebra, but as we start, like we have to understand that this is a mathematical methods for like physicists course, right? So a kind of mathematical physics course. So at each stage, it is required to motivate why a particular subject is required, like how linear algebra comes into picture here. And what I have decided is I will give you its relevance to a number of physics problems. So maybe we will look at examples from maybe day-to-day day-to-day observations. So first of all, like whenever we are talking of linear algebra, some of the quantities that we must be very much well aware of are the following. So you should be aware of scalars, you should be aware of vectors, and you should be aware of a kind of more universal object which we call tensors. So in fact, what happens is tensors, like tensors are objects which are a more general form of scalars and vectors. So you can say scalars are rank 0 tensors, vectors are rank 1 tensors, and tensors can be of any rank. Okay, so these things will become much clearer when we have a physical picture for objects, like physical objects, which are scalars, vectors, and tensors. So like scalars, you can see quantity like mass, right? So mass is a scalar. It has a given value. It has a given numerical value. Okay, and this numerical value could be like in a like rigorous mathematical sense. This m can be a real number. Okay, and similarly, like you can have another quantity like charge. Okay, so this is mass, this is charge, and similarly you can think of other quantity like, so accordingly q can also be a real number, and then we can think of another quantity like T, which is say temperature. So let's just bring them a little below. So like these are pure numbers. Okay, so mass is a number, charge is a number, temperature is a number. We can also instead have quantities which are vectors, like for example velocity vector. So this v will contain in so it would be a collection of 2 numbers or 3 numbers or 4 numbers depending on the dimension in which you are looking at. So let me just correct it. So this could be a number like n, Rn. Actually, that's not a very accurate representation. So let's first, for the time being, let's go ahead with what typical velocities we are imagining. So suppose we fix a coordinate system with unit vectors say x1, x2, and x3 along the 3 directions. Then this velocity could be written as, so it could be v1 x1 cap plus v2 x2 cap plus v3 x3 cap, and it can also be represented . by a corresponding row vectors with these three quantities as members of this column. So it can also be represented as a column vector with elements v1, v2, v3 there. So this can realistically represent a vector v, okay, in a three-dimensional space. But then in various scenarios, you may require these vectors to be of a higher dimensional quantity. So they need not necessarily be a three-dimensional quantity. So in general, n dimensions, where n is a number, n is a whole number. Okay, so similar manner, like acceleration a could be also represented as a vector. And on the other hand, we also come across quantities which are tensors in real life. So which requires a little bit more motivation. Why do we require tensors in a physical scenario? So suppose, like as an example, say consider current flow in a semiconductor. Very soon I will come to like the manipulations which are required, or the kind of math that needs to be developed. But before that, let us just kind of familiarize ourselves with y tensors. So the question is here, y tensors in physics. Okay, so let's imagine that we have a vector J, which is the current density. And we have a particular sample which is three-dimensional in nature. So this current density J is flowing. So J can be understood as 1 over cross-sectional area of this current. So suppose a current I, this current I is the same current which we imagine in Ohm's law kind of a scenario. But I am representing it as a vector because this current can flow, can have a directional sense. Okay. So now suppose an electric field, an external electric field. So E is an external electric field. So E is an external electric field which acts in a direction as shown in this picture. So then, in general, this current density J could be written as a quantity sigma times E, right? So E again is a vector with three components, Ex, Ey, Ez. So this you can consider as electric field strengths along the X direction, along the Y direction, and along the Z direction in an XYZ coordinate system. So suppose we imagine a XYZ coordinate system. Then this Ex, Ey, Ez are the electric field intensities along the x direction, y direction, and z direction. And this J can also be considered as currents which are flowing along the x direction, along the y direction, along the z direction. So in a realistic scenario, current will flow in all the three possible directions in a realistic sample, and electric field could be arbitrarily aligned along any of these directions, and accordingly this sigma has a structure so sigma has a structure such that you can see that the current density J is given by sigma times E. So this is now a quantity which is a tensorial quantity. Okay, and this occurs in nature every now material that you take, right? If you apply an electric field, the current densities will act in arbitrary directions. So for example, suppose let E be only Ex x cap. That means in this notation it is only Ex 0 0, right? And let sigma be a quantity, so which is like say some number sigma 1, some number sigma 1 and sigma 2, 0 0 0 elsewhere. So therefore you can see that the sigma times is going to be sigma 2, sigma 1, sigma 1. Okay, let's mark it sigma 2, 0 0 0 0 0, and then a Ex 0 0. So this would be like sigma 2 Ex, sigma 1 Ex, and 0. So therefore you can see that although electric field was acting only along the x direction, but current can actually flow along both x and y direction. So these are very much realistic scenarios which occur in daily life, and therefore we need to handle tensors. We need to be able to handle tensors. So in this case, this is a second rank tensor. So this one is a example of a second rank tensor. Let me give now. Let me just to keep the mathematicians interested. So this is kind of an example from physics. Let's give examples from a completely different perspective. Say example from machine learning or optimization. Just to make sure that overall you get a general feel of the subject. So, like you would have seen that, say, we have to train computers to identify like simple things like numbers visually, which as humans we are able to identify very easily. Okay, so like suppose we have a number like 5. So we have a character 5. Okay, so in general, now the task is input so input this thing as a image. So input, so this one is an image, and ask the computer which number it is. Okay, so in general, like computers only identify uh, like a sequence of bits or a sequence of information. Okay, so like this 5 actually could be written in many ways. So therefore, the computer has to be first trained onto various types of writing file by various individuals. Okay, and then when you give it another fresh input, it should be able to identify it. So how would you really make the computer understand what 5 is, or how would you input this image? So how would you input images? So this is done by an interesting manner. Okay, so let me see how these quantities come back again. So suppose we have a quantity written as 5. What we do really is divide this into grids. So suppose we have divided it to 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So here it is a 15, and here it is 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. So we have divided it into a 15 by 15. And each of these units, like we call a pixel. Okay. So we make a 15 by 15 grid, and we call each of these as a pixel. Now, like this number 5 could have been any other image for that matter. It need not necessarily be the specific image. And each of these grids can have values from 0 to 2 to the power 8 minus 1. So this is for 8-bit computing. Okay, so 2 to the power 8 minus 1, that means that, say, at this location, the pixel could have been 255. And at this location, the value could have been 0. Right? So it can have any number between 0 to 255 in any of these pixels. And 0 to 255 just indicate the strength of the like pixel. So suppose we have a more complicated picture. Say, suppose instead of 5, we had a more complicated picture, say map of India. Then map of India would have had a specific number of like specific number of pixels, and each pixel would have had a number from 0 to 255. So suppose we are using a 16-bit computing, then these numbers could have been between 0 and 2 to the power 9, 2 to the power 16 minus 1. Okay, so 2 to the power 8 is, yeah, 2 to the power is 8 is 256, so 256 minus 1 is 255. So between 0 to 255, we input a number. And then, like, what we can do is, we can have this either as a (15 cross 15) tensor, right? Okay, so let me write, instead of tensor, write 15 cross 15 matrix. So you can represent this image as either as a, okay, either as a 15 by 15 matrix, or you could have represented it as a 225. 15 cross 15 is 225 dimensional vector. Okay, so a three-dimensional vector was the kind of thing which we saw here. So in this case, Ex was a three-dimensional vector. This was a three-dimensional vector. Right. In this case, this could be a 225 dimensional vector. Okay. And how would you do it? So basically, the process is, okay, the process is basically to, like, how would you unroll it? So unroll the matrix into a vector. Okay, so how would you do this? So basically, you can take this entire chunk, like from here to here, and put them as the initial member of this vector, and then you can take the next chunk and place it below this, and so on. You continue till you have a 225 dimensional vector. So therefore, this is how quantities like vectors and a three-dimensional like quantity like matrix enters into, even when we are trying to do machine learning or optimization problem. So an optimization problem could be formulated as, so suppose you have a test data set. So a test data set could be like, so you can have a 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. You can also write 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. You can also write it as 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So depending on, you can give, so test data set and so on, right? You can, so where this is one set of 0 to 9, so you train your algorithm to identify 0 to 9 out of this test set, and similarly kind of you can give a sorry, test data, and they should be called the training data. So you can kind of train the algorithm to understand these quantities 0 to 9, and then you can put a test character. So this could be a test data, and then identify whether it is or whether it is 0 or whether it is 8 or 9. So over there also we are requiring methods to basically. So what I would do is I would kind of add some pages here. Okay, so therefore, like this is another place where you are kind of requiring vectors and matrices. You could also have asked a quantity like 0 or 1. So suppose if it is 5, the output could be 1. And if the character is not 5, then the output could be 0. So zeros or ones individually are scalar quantities. So accordingly, even in a field like machine learning, you come across scalars, vectors, and kind of matrices, and they together fall into kind of tensors, and that's why the name TensorFlow for the trademark. Google machine learning software. Okay, so that's the reason why you are calling it as TensorFlow. Means that's what people call TensorFlow. So let's now take an example which is kind of slightly more uh, understandable even for students who would have studied kind of physics only at +2 level and later on would not have gotten an opportunity. So let's consider this example of a harmonic oscillator. So simple harmonic oscillator, and over here we will go into a version which would be a coupled simple harmonic oscillator. We'll soon come to what it means. So this basic system is a mass m connected to a spring of spring constant k, and it is given a deflection x, right? And then once you deflect it by an amount x and then you release it, so then it will undergo oscillations about its mean position, and therefore like the task is how would this behave. So we know that this force, like if you are pulling the mass with a attached to a spring of spring constant k, there is a restoring force minus kx which acts, and therefore like because the mass is m, so we know that force is also given by mx double dot, where these dots are representing time derivative with respect to acceleration. X double dot is essentially second time derivative with respect to second time derivative of x. So therefore x double dot is acceleration, and mass into acceleration is the restoring force. So what we have used is nothing more than Newton's second law here. And therefore we see that like this takes a shape of d2x dt2 equals to minus kx. So this is a second order homogeneous differential equation for scalar x. Right, so this is basically a like simple second order differential equation. You would have solved it many a times. I would not get into solving this at this juncture. My idea here is to kind of generalize it to a slightly more involved problem where you will see how the vectors creep in, vectors and tensors creep in. So now what we do is we consider two masses here. For that matter, it could have been any number of masses, and with stiffnesses K1, K2, and K3, spring constants K1, K2, and K3. And in a similar manner, what we'll imagine is this mass would be deflected by an amount x1, and this mass would be deflected by an amount x2 with respect to their equilibrium position or with respect to their rest position. So now in a similar manner, we can write down the equations of motion as mx1 double dot. So because when we kind of deflect the first mass by x1 towards the right, there is a say if we imagine the force direction to be along the positive direction, so spring K1 is stretched and therefore it undergoes a restoring force in the negative of this arrow direction, and therefore this would be like minus K1 x1. Okay, and then we have another part which is like, so because we have pulled this spring, right, so it is like now the force is as if like whenever we are like moving the mass m by a distance x1 in the direction of k2, k2 is compressed by an amount x1. At the same time, because the other mass is stretched, like the other mass is again deflected by x2, that leads to stretching of spring k2. So basically k2 undergoes a compression, so x1 minus by an amount x1 minus x2, and then like there would accordingly be a restoring force which is like minus k2 of this. Okay, in a similar manner, we can write down the equation of motion for mass, the second mass, where the deflection is x2 double dot. In this case, the spring K3 is compressed in the positive x direction. So if this is the positive x direction or the force direction, so then the restoring force is in the opposite way. So therefore, it undergoes a K3 x2. And then because it is stretched by an amount x2, and x1 was the deflection of the first mass, so that is the compression of k2. So the spring k2 is stretched by an amount x2 minus x1, and therefore the restoring force again is in the negative direction of this. So therefore, you can cast this now as a set of two equations, which will read as mx1 double dot mx2 double dot equals to, so now we have in terms of x1, so minus of k1 plus k2 of x1 and minus plus k2 of x2, and this would be minus plus k2 of x1, then it would be minus of k1 plus k2, k3 plus k2. So it's like minus of k2 plus k3 of x2. So therefore, you can actually write this as m0 m x1 double dot x2 double dot equals to minus of, then we can take k1 plus k2, and here you can take k2 plus k3, and here it is minus k2 minus k2, and then we'll have a x1 x2. So as if like this whole thing is now represented as a matrix M. It's like with a column vector x. So here x is x1 x2, it's a two-dimensional column vector, and then it is equal to minus of some matrix K times X. Okay, so what you see here is, again, you have tried to represent, like, while trying to solve a slightly more them than like simple harmonic spring mass system. When you added more spring, it is a situation where you now have mx double dot, now where m is now a tensor of rank 2 by 2, like of rank 2, but then the dimension is 2 by 2. So now there is something called rank, something called dimension. So when we are writing this m0 m, so it's a 2 by 2, but what rank tensor? Scalar is a tensor of rank 0, vector is a tensor of rank 1, and this is a 2 by 2 tensor of rank 2. It's like, so let me just for clarity say that this one, yeah, this is a 3 by 3 tensor of rank 2. Okay, so rank is basically like, so suppose we are requiring to represent these in a kind of as frames. So how many kind of indices do we require to represent this quantity? So we require basically two indices to represent these quantities, and that's why subscript xx, right? Whereas the dimension, so this 3 is basically a dimension, and this one is leading to rank 2. So that, okay, so therefore now you have converted this into an equation in terms of tensors, right? The same physical problem has been converted into tensors. So just to kind of recall how we kind of how we can have higher rank tensors. So let us imagine now, so higher rank tensor. Take example from that ML problem. Right, but this time what we do is the image now is a fancy image. Yeah, this is fine. So now the image is basically a color image. And therefore, like if we are dividing it into a, say, a similar way as a kind of like the previous problem, if we are dividing it into a 15 by 15 pixels, right? So each pixel can be represented by three numbers, each for R, G, and B. Okay, so like this is how color is represented. Like so, basically, what one does is each of these R, G, and B will have a specific numeric value, and a combination of R, G, and B will tell you which color it is. Okay, so therefore, this image can be represented by a tensor of rank 3. Right, so earlier it was a rank 2 tensor. Say the conductivity tensor was a rank tensor, but now it is a rank 3 tensor. And now we have these numbers as, say, so it would be a 15 cross 15 cross 3 object. Okay, this as if this image goes as kind of layers. So 3 layers, right? One for R, one for G, and one for B values. And it would again be a 15 by 15 layer, right? So it is like the same quantity can now be represented by 3 layers. Now suppose, so this was a color image. Now suppose the same quantity you want as a function of time, say for a video, right? Then time would be the fourth quantity. So therefore these images for, so similarly we require rank 4 tensor for videos. So the fourth index is given by the time index now. So the two indexes are the x axis, x direction and y direction, like pixels. So the pixel along the x direction is kind of 1 to the rank. The y direction is contributing another 1. These 3 layers is contributing another 1. So that becomes a rank 3 tensor. And now if you have a fourth index, which is basically the flow of time, because these colored images will change as a function of time. Therefore, that would be corresponding to the like rank 4 tensor. So that's how like these tensors, which are kind of crucial ingredients in linear algebra, that show up in various physical problems. I would say even these machine learning problems are physical problems, right? So like that's how I think I have given enough motivation for why tensors are required, or why tensors. Just to give you some background into how this problem was solved, or this problem would be solved, or what it yields, I'm just to kind of write down this in a slightly do a couple of more steps over here. Dot equals to minus k dot, and always multiply by m inverse on both sides, like 3 multiplied by m inverse on both sides, and I can get an equation. It's like x vector double dot is minus m inverse k x. But from our earlier idea for a one-dimensional case where we had a mx double dot equals to minus kx, which can also be written as x double dot equals to minus omega square x, where omega square is in a similar manner, like should have by a of unit like identity tensor or identity matrix here, and that would lead to x double dot equals to minus omega square along the diagonal elements times x. Therefore, like you go over to an equation which reads like m inverse kx equals to omega square x, right? And because x double dot was minus m inverse kx, and x double dot is also minus omega squared identity x. So therefore, m inverse kx equals to omega square x, and this converts into an eigenvalue problem now. So it's like m inverse k minus omega square identity times x is 0. So for all non-trivial x, right, this expression has to be satisfied. So in our specific example, M is given by a matrix M00 M. So therefore, it is very easy to see that M inverse would be 1 over M, 1 over M along the diagonal uh, elements. So that is basically something from Cayley-Hamilton's theorem. So we will get a chance to see that later on. Here I am just trying to show you the strength of these kind of methods in physics. So therefore, K matrix was already known to be this quantity. So M inverse K becomes a quantity like this, right? And thus, determinant of M inverse K minus omega square identity equals to 0. This will imply the following determinant equation, and that will lead us to a quadratic equation in omega square, like as shown here, and accordingly omega square would be given by the following two numbers, right? So we can have omega square, one frequency which is a higher frequency, so this is a higher frequency, and the other which is a lower frequency. Okay, so for the higher frequency case, let's imagine eigenvector. So this is a kind of test eigenvector. So this is just an assumption. Say, suppose the eigenvectors have components a1 and a2. So then this must satisfy the eigenvalue equation. So it's like m inverse k times the eigenvector. So this is just telling us that m inverse k times the eigenvector equals to omega square, because omega 1 square is the eigenvalue here, times the eigenvector. So that will lead us to a value like a relationship between A2 and A1, where it says A2 equals to minus A1. So if you are looking for a normalized eigenvectors, this is going to be the normalized eigenvector corresponding to x1. So therefore we have like corresponding to omega 1, there is a normalized eigenvector which is 1 minus 1, 1 over root 2. And this we will represent using something which is called ket of EB. So this is the pronunciation, or this is the symbol which we will be using in this course. So the ket is always a column vector, and the dagger of ket, so dagger of ket is basically a row vector EB. Okay, so like this would be the notation that we will be using. People use different types of notations around. So therefore, like EB would be this. Similarly, for the lower frequency case, we can write omega 2 square is k1 by m, and accordingly x2 is equals to b1 b2. This is an assumption, or this is a test case, and accordingly we can write the eigenvalue equation. So this is the corresponding eigenvalue equation, and we can see that b1 equals to b2 equals to b is what results, and accordingly the normalized eigenvector is going to be 1 over root 2 1 1, and this we identify by a ket ep. So this is like a ket ep, and accordingly its kind of conjugate would be, or its transpose conjugate is going to be EB as shown here, and it would be a row vector. So corresponding to a column vector, when you transpose conjugate it, it becomes a row vector, and accordingly EP is going to be written like this, and EB is going to be written like this, and then we can accordingly do a completeness check of completeness condition. If this sum is an identity matrix of suitable rank and dimension, then EP and EB will form a complete set, a complete basis. So because this is 1001, which is the identity of suitable rank and dimension, so therefore EP and EB form a basis set, okay, of vectors in this given vector space. So that way what essentially they represent is, so you can imagine this EP and EB. So this is the corresponding ket vector, and this is the corresponding ket vector. So they respectively represent the pendulum mode and the breathing mode. So when we say pendulum mode, it is as if both x1 and x2 are in phase. So either they both go like this, or both come back like this. Okay, so that way this is both the masses are maintaining a constant phase relationship, and then they move together. Whereas in the breathing mode, what happens is F1 and if mass, the first mass is going to the left, the second mass will go to the right. And on the other hand, if the first mass goes to the right, the second mass goes to the left. So this is as if something is kind of coming closer and going farther. So this you can imagine as breathing, right? So therefore this is called a breathing mode. And any displacement, the beauty is that any vector can be represented as So any specific displacement or any time snapshot. So this would be any time snapshot can be represented as a linear combination of EP and EB. So that's how, and this is something which is what we have done essentially is a like something called the modal analysis for this problem. So we have found out the modes of vibration and the corresponding frequencies for that. So in this case, because EP corresponded to an omega which was larger, no. So what happened is this is EB. No, omega p corresponds to a frequency which corresponded to pendulum mode. So therefore, this one is going to be a, so pendulum mode is going to be a low frequency mode, whereas the breathing mode is going to be the high frequency mode. So now after this much of basics, like trying to motivate that really we are coming across scalars, we are coming across vectors, we are coming across tensors of various rank in real life. Now it is worthwhile to get into the formal theory for these scalars, vectors, and tensors, and that forms a field in mathematics called linear algebra. So we will be doing it at a more kind of in a more detailed manner, the way mathematicians would like to do, or basically the way applied mathematicians would like to do, or physicists would like to do. So we will go ahead with linear algebra in the next class. Okay, so thank you. So I would like to end the class today, right now here. So the questions regarding having a tutorial. So can we possibly meet in the weekend sometime? Is it possible for everyone to meet in a weekend? So Saturday,
Okay, sir.
comfortably
sir.
we can do these tutorials, because see, academic section has asked us to have some kind of a meeting session every 1 or 2 weeks, common meeting sessions. So I would rather like to kind of put it in a formal manner as some kind of a tutorial session every 1 or 2 weeks. So once in a while we will try to do that. So let's do our first tutorial session this Saturday. And because it's a holiday, otherwise, even if it extends beyond 1 hour, I hope people would be able to find some time. I would try to restrict it to 1 hour, but in case it exceeds a little bit, you people please try to accommodate. Okay, and I would
Okay, sir.
specially request the two students like Rishabh and Ashna from maths, because they have written to me some of the basic problems that they are facing. They are in general saying that the other math students would also be facing. So we will try to address those, as well as some of the questions which I guess Arpita asked today morning. So we will try to address some of that. So in general, both of these done together should take care of all the doubts or all the confusions which had happened during the first week of